Hi everyone, and welcome to the Mat 211 review of mean, variance, and standard deviation. My name is Julia, and I work for the tutoring centers at ASU. So, investments in junk bonds are declining at a continuous rate of 5% per year. How long will an average dollar remain invested in junk bonds? So in order to solve this problem, we first need to know what sort of distribution we're looking at. Now, this is an exponential distribution because we're looking at the time in between events for a Poisson distribution. So, for instance, if you think that every time a dollar stops being invested, that's, a length of time, and the count of those dollars would be a Poisson distribution, then the time in between each of these dollars no longer being invested is an exponential distribution. So exponential distributions have a couple of things. The main parameter here is what we generally term as lambda, which is the rate of the distribution. So that rate is going to be our 5% here, but we're going to write it as a decimal, so 0.05. So once we know this, there's a quick shortcut to find the average. So when we say how long will an average dollar remain invested, we're talking about the average length of time that this dollar will be invested, or rather that the average length of time in which the investment declines to zero for this dollar. So the shortcut is that our expected value of x, or our mean, here where mean is in years, is going to be equal to 1 over lambda. So this means that we have 1 over our 0.05, and this equals 20, or 20 years. So that's actually our answer. But I do want to go over the other way of looking at this, just in case you're given the distribution or the probability density function instead of, the rate. So that way you can find it using the probability density function as well. So the probability density function for an exponential distribution is f of x equals lambda times e to the negative lambda x. Now then, remember that in order to find the expected value from a probability density function, we need that the expected value of x is equal to, oops, let's erase that, is equal to negative infinity to infinity. Let's write that so it doesn't look like a weird 8. Infinity, there we go, a little better, of our probability density function times x dx, which in this case, note that we can't have negative years here. We can't go back in time, so we don't want negative infinity here. We actually want 0, but we can go all the way up to an infinite number of years, so we do want infinity here. And our distribution here is f of x equals lambda times e to the negative lambda x, which in our case is going to be 0.05 times e to the negative 0.05x. So we'll write that in over here, 0.05 times e to the negative 0.05x times x dx. Now, this is a integration by parts case here. We know this to be true because if we look at our distribution, or we look at our integral here, we have this function of x times this function of x, and neither of these is part of the derivative of the other. So we can't make one of them disappear by integrating the other. So instead we're going to have to do an integration by parts here. Now, as a reminder, for integration by parts, we have, so if we have some integral of u times dv, where these are both functions in this case, then this is going to be equal to u times v, again, both functions, minus v times du. So we want to assign one of these to be our u and the other to be our dv, so that we can then solve for the parts in the other side of our equation here. So let's go ahead and set, there we go. Let's go ahead and set u equal to our x. So this is going to be our u. And we're going to set dv equal to this 0.05 times e to the negative 0.05x. This will be our dv function here. X, there we go. Now we want to take the derivative of this one, so that's going to be du, which equals dx in this case, because we want to carry along the differential. And then we want to have v, we want to figure out v from dv here, so that means we're just going to integrate this, or just take the antiderivative of it. So our v here is going to be negative e to the negative 0.05x. And you can check this to make sure that this is true. The negative comes from this negative here being divided out when we take the antiderivative of dv. So now this means that our whole function here is equal to, we'll just bring this down over here, it's going to be equal to 0 to infinity of, nope, that's the function. So it's going to be equal to u times v. Let's just draw a little line over here so we know what we're talking about. Boop. So u times v, where u is x and v is this negative e to the negative 0.05x. So we'll have x times negative e to the negative 0.05x. And since this is a definite integral, we're going to need to evaluate this from 0 to infinity. Then we're going to subtract from it our v times du. Well, dv is our 0.05, or excuse me, v is our negative e to the negative 0.05. So negative e to the negative 0.05 x times du, which is dx. So we can go ahead and integrate this from 0 to infinity as well. This gives us, well, this side, we'll just bring the negative out to the front here. Negative x e to the negative 0.05 x evaluated from 0 to x minus, well, if we take the integral of, or if we look at the integral of this is going to be e to the negative, oops, I'm running out of space here. Let's make this 0 smaller. Let's put this 0 on this side. There we go. So e to the negative 0.05x over 0.05. And we're again going to evaluate that from 0 to infinity here. So we can combine these two. That's going to give us negative x. And actually, let's go ahead and erase the top part up here, and we're going to combine them back up at the top so that we don't run out of space here. We'll just erase all that. Erase, erase, erase. There we go. So we're coming back up. Up to here. So this is going to equal, if we combine these two together, since we're evaluating them at the same range, we can combine them. This will give us negative x e to the negative 0.05x minus e to the negative 0.05x over 0.05. And that's from 0 to infinity. So now, since we have an infinity as one of our boundaries here, we need to use a limit in order to solve for this. So I'm just going to erase and make myself some space here. There we go. This is going to equal then, well, this part is, so we're going to start with the infinity here. So that's going to be a limit as x goes to infinity of this whole function here. Negative x e to the negative 0.05x, that's a 5, minus e to the negative 0.05x over 0.05. And then we're going to subtract from it this function evaluated at 0. So that's going to be minus negative 0 times e to the negative 0.05 to the 0 minus e to the negative 0.05 to the 0 all over 0.05. All right, so this looks like a lot, but it's actually not so bad. Notice that since we have this e to the negative 0.05x, as x goes to infinity, this exponent here is going to get increasingly small, so really far out in the negative range. And that means that e is going to get smaller and smaller and smaller because this is a negative exponent. So therefore, as x goes to infinity, both this e to the negative 0.05 and this e to the negative 0.05 are going to go to 0. So this whole limit here goes to 0. Boom. Now we're going to subtract from that this guy. Well, we have minus, well, this term goes to 0 because we have a 0 here, and everything it's multiplied by is a 0, so we got a 0. And then that's going to be subtracted from, well, our exponent for this term, for our e, this is going to be e to the negative 0, so it's just going to be e to the 0. Since we have it, negative 0.05 is multiplied by 0. And so anytime we have e to the 0, this is equal to 1. So we're going to have 1 over this 0.05 here. So that means that we actually just have 1 over 0.05, which we know from before is equal to 20 years. So that's it. 20 years. We did it the easy way, which you should definitely remember, and we did it the hard way, which was fun, but took a lot longer. So before I go, I just want to remind you all that if you're looking for any additional tutoring or academic support at ASU, you can go to the Tutoring Center's website, tutoring.asu.edu, to find all of our resources. Also, if you're looking for tutoring for your specific course, you can use our tutor search tool, which you can find off of our main website page here, or by going directly to the tool at this full link on the screen. So thanks so much, and have a great rest of your day.